When it start, everybody will start. 3, 2, 1, start. So this is, good morning everyone, so this is Fourmions solution to the second problem. So first of all, full screen. So first of all, we have the conditions, the kinematic conditions that we have taken here for linear solution. The water is being poured from a height which is around the order of 10, and then we have performed the kinematics here. And according to that, we have found out the wave number here. The wave number which is basically the inertial term divided by the surface tension, which comes out to equal to 110. This completely overshoots the convective instability condition, which is at 1. So from here, we make a correction to the initial report that we stated that Bridgman's idea is partially correct. It is completely wrong. And the pattern that we have here, the lambda is equal to 9.1 r is selected in both regimes, and the pattern sustains in both the regimes, and the V1 number comparison can be seen here with the standard convective instability normal. So now we come to the geometry of it, that why the cylinder is unstable. So first of all, when the lambda exceeds 2 pi r, the cylinder becomes thermodynamically unstable, and it is an evident knowledge that for us here, the surface area will be reduced, so the flow would try to change itself into a sphere, and that would cause the formation of bulges. Now, when the bulge is formed, of course, according to the Laplace equation and this linearized curvature perturbation, we see that perturbation condition, we see that as the bulge is formed, the radius of curvature increases, and because of that, the pressure inside falls, and because of pressure, the fluid from the surrounding area flow into the bulge, and that would cause the instability. We have also shown the stability by the 3 modes. And we have shown the deepest point here, which we can take from all this geometric discussion, that there will be a simultaneous destabilization at n equals to 0 at long wavelengths, and the stabilization will be and it will be completely stabilized for all modes which are greater than 1. So, the next. So now we have the governing equation. First of all, we have the incompressible Navier-Stokes and the incompressibility condition. We take the slender jet condition here, which basically states that the for this particular flow, the radius will be much smaller than the length parameter of the flow that we are taking. So in this case, the azimuthal term of the incompressible Navier-Stokes will dominate. And based on this slender jet approximation, we have done the calculation of the continuity here, and then we have taken the area average momentum condition, and we solved the Navier-Stokes based on this slender jet approximation, and we have added this proton term here. So now then we have the perturbation strategy to linearize the Navier-Stokes equation, and basically these are the 3 variables by which we will be defining the regimes: the Reynolds number, the Weber number, and the Massage number. This is basically Reynolds number is the inertia by viscosity, inertia by capillary action, and the viscous diameter. Now the 2 modes that we are interested here is the n is equal to, which is the axisymmetric mode, and the which basically shows the really plateau instability and goes for less than, we will discuss it later on. And then we have the azimuthal condition for n greater than 2, where we have this perturbation form that we will be using. And the glass slip inside, this is a critique that was given to us in the report. So we have mentioned that the glass slip is effective for elliptical surface in which both n equals to 0 and n equals to 2 mode are present simultaneously. Next. So we have stated in the report as well the model assumptions. We have stated a few validity here. The gravitational thinning we have not accounted for in the report, so we have added it here. These are limitations of the assumption that we have made. Like the radius of the flow would be thinning with gravity, and then the glass slip, which was also rightfully critiqued in our report as well. So we have added that correction here too when I contract an elliptical velocity profile. And then we have the nonlinear pinch off, which we have also added, which would happen which would happen gradually as the flow continues. Okay, next. So now these are the boundary conditions that we use to solve for this linear perturbation condition. The kinematic boundary condition basically says fluid cannot cross the surface, and we have added this surface derivative here from the velocity potential, and then we have calculated this term here. And then the dynamic boundary condition, we have used the normal condition of the Young Laplace, and then we have taken the condition that if in a given fluid at the edges there cannot be a shear stress. So we added that tangential condition here, and from the viscous damping coefficient. Next. these are the derivations, the steps of the derivation. We have only added this final ODE, linear damping ODE into the report. But these are the steps where we have gone. We have taken the curvature form of this, and then we have done the solving of this Laplace equation to get this format, and then we have added the radial ns, from which we basically add all the terms, and we form the ODE. And here we have the most importantly, we have the critical viscosity condition, for which where the fluid flow moves from the underdamped to the overdamped phase. And these are the conditions for the different jet characteristics that can be seen. We see that trivially for n equals to 1, the jet will be neutral, and then from there you can see stable flows. So now where do we get the lambda max equals 9.01 R condition? So we get it from the linear dispersion relation where we have this Bessel function, and then we define the growth rate here. So from here we have this function of this area of the growth rate, which we are maximizing by df by dx. On solving this, we get this form of a transcendental equation, which when we solve numerically, we get this form where lambda is equal to pi r divided by 0.697, which gives us 9.1 R. And this is the point where the growth rate of the jet will be maximum. And for kr is equals to 0, as we have mentioned here, that is the optimal compromise here. Right now, we have this is an experiment that we have actually done for So for this is the condition that we have taken: the jet radius to 4 mm, the lambda to be on 36, comes out to be on 36 mm with calculation. So now if you show the photo, previous. Yeah. So that is around 3.29. So we see that 3.29 centimeters. So from 3.4 to 3.29 centimeters, we see that's a reasonably good agreement. Next. So here we have the growth rate curve, where we basically show the plateauing condition for the unstable and stable regimes. We see that for t less than 1, the growth rate is greater than 0, so all along the waves are unstable. And for t greater than 0, the s equals to 0, yes, we have a stable oscillation, and the short wave suppressed wherever short waves that are the short waves in the jet will be suppressed by the surface tension. So we get the maximum growth condition at the peak, and we see that these are the characteristics of the curve that we have defined. Okay. So this is basically a change of Onnes's number and change of the on the wavelength according to that. Right. These are the different cases that we have shown that the characteristic remains same, only the wavelength changes. Yeah. So this is the convective instability. We have shown the two cases where we are defining the convective absolute stuff here, and we have seen that this is basically what Vinay is seeing here, and this is the absolute current where the grows in time and the waves remain uniform in space, and this is what basically will be seen by Vinay on the jet. Move on next. Yes. So these are the quantitative predictions that we have done the calculation. These are all the scaling laws that can be implied and can be done in experimentation. And these are the variables that we have used. Move to the next. And here this is the simulation methodology. A short note on the simulation methodology and the ODEs that we have created. And these are the methods: the ODE 45 standard solvent for RT45. And these are simulation parameters that we have taken, which is different from the experimental parameter. Note that these are different. Move to next. Yes, so here we have the underdamped regime, as we have discussed about it earlier, right? At the azimuthal modes, and these are the parameters that we have shown here. We have shown the quality check, and we have seen that there is a good agreement of around 2.8 in this region. Right, the Onnes's number has been stated, and these are the jet flow characteristics according to the theta. And you can see the underdamped characteristic can also be seen here. For n equals to 0, there is a exponential growth. There is a bulging, and as we have mentioned, that it remains stable. That is the instability condition. The wave persists. Now we will move down. Here we have the overdamped region. Okay, an overdamped region, Onnes's number is around 2.3. So these are the conditions that we get, similar to that. Let's move down. Okay, these are the theoretical standings we have here. Next down. These are the similarities, and then we have the exotic patterns where we have done a superposition. This is the basically to find the exotic pattern. We have got these exotic jet cross section, and these are the basically the formulation that we have done. This is the characterization of R. Let's move down. These are again the exotic patterns that we have done for initial angular momentum, and we can see that it is turning in a helical form. The jet characteristics here. Move down. And this we have done a direct orifice oscillation, application of which we find in jet printing. We have basically added a forced oscillation term to the differential equation. These are the jet characteristics that we get. And this is the optimal frequency, forcing frequency 1 equals to 0 that you have maintained is 39 Hz. Move down. And then we have the Matthew resonance here, which we have basically done that we have perturbed the lower
whole system.
Yeah, we perturb the whole system here. And thus the practical tongue here and the entire parametric modulation that we are getting here is this. Okay. And this was first done by Savard around 200 years ago to the same experiment. Okay, let's move down to get uniform drops. And these are the limitations of our model that we have got from the we have corrections from the examiner's feedback. We claim that one number is less than 1 for Uniqueass score, but actually it's around 110 as we showed in the first slide. And then we have also made comments on the convective instability. We stated that the jet survives. That is wrong. We always say that the jet always breaks, but that happens further downstream, and the simulation parameters are not stated in report. Also, a point to be noted is that the Ritishman's case would still have some merit left if we are considering a higher viscosity liquid, but since we are considering in this model mostly of water or lower viscosity liquid, therefore Kinai's perspective remains valid through and through. And here we have the inherent model limitation that was stated, that is the orifice geometry, the glass slip, and these are the limitations that again were mentioned in the report, and these are the non-linear effects that we see as satellite drop and pinch off. Outside the non-linear effects which are not discussed enough in the report, gravitational thinning. Let's move down. And these are subsequent developments that we have made. These are the experimentations that are recommended, and simulation verification we have done. The physical experiment has been made, and we placed in the AI regime and selectively both way. Pattern is real in either case. All scaling laws are unaffected in both the cases, so his prediction remains valid through and through. Let's move down. And thus you have the conclusion that the British one is wrong, the pattern is real, and Kinai's score we have wave number 110 which goes spatially, and these are the characteristics of the wave, and these are three variable predictions, the known spacing, mode, and the pattern in the linear intersected dominant mode of the Rayleigh pattern instability is not an illusion. Let's move down, and these are the references.
So, because it's important, when you are presenting, first thing is you should face the audience, not the slide, and you should not stand in front of the slide because it might block you.
It goes to everyone. Please, this is not the way you slide. You present it to anyone. You should look at the audience, because you are not supposed to look at the slides and read out. You're supposed to communicate with the audience. You're not reading slides. Please.
I mean, if you need to look at the slides, what you can do is to stand a little bit right or left of the screen, and then look at the screen if you need.
And you can even take a presenter's note in a tab or something, or paper, anything.
And remain like to one side of the screen, so that like even if you are looking at the screen, it doesn't look like you are reading from the screen. It looks like you are still facing the audience and but reading from. You can look at the screen. That's not the problem. Remain a little bit to the side.
Okay. Projectile dysfunction. You have 1 minute to prepare, and then we will start that time. But you can introduce if you want.
So we are doing projectile dysfunction. We are 4 members. Me, Nitish Patil, Madhavi Sharma, Mekul Agarwal, and Govind Agarwal. So we are going to provide a constructive critique on the.
Before start, ready? When I say start, and start the timer, then you can start. 3, 2, 1, start.
Okay, so we are going to provide a constructive critique for the presentation given by Team Fourmions on the problem 2. So basically, first some remarks from the report. In the report, they basically use this. First, they solve the Navier-Stokes incompressible solution, and then they extend it to the harmonic oscillation term. So it would have been better to first isolate the individual harmonic oscillation term and then have to discuss damping term as a damped oscillator. Then secondly, the n equal to 0 mode, which is presented as a particular new solution in section 2.4, is actually covered by Rayleigh extension. It's basically follows the same mathematical framework of r plus epsilon cos nz. So it could have been extended to that. And the harmonic dependence of the epsilon term, it depends harmonically on time, has also been extensively discussed by Rayleigh, but not discussed in the presentation of the report. So it could have been stated that in an equal to zero mode, the epsilon term harmonically depends on time. Also, the report extensively talks about the R by L being much less than 1. So, the original paper by Rayleigh and both Plato, they address the condition of R by L more than 1. So, it was a good opportunity for some extra further work. Using Bessel function, they could have given a reference for that. Also, some remarks on the presentation. It would have been better if they also added a particular experimental result on the head of water dependence on the H and lambda, because there was no particular point where they showed that the lambda is proportional to V. So it would have been good if they also showed how the pressure head, the root of the height is proportional to the lambda.
Since we have a lot of time, what is head of water?
Basically, the height of the pressure head at the orifice. Yeah.
Does the jury have any other questions? Does the audience have any other questions? Does the team Fourmion want to clarify something?
Yeah, we wanted to clarify that the pressure head.
This height of water.
The height of the water.
Clarify. This.
Okay. So, if you are planning an experiment on this, how do you think we can measure the parameters, and how do you think we can do this?
Rayleigh has extensively documented that he used dividers to measure the wavelength and a particular setup to measure the pressure rate. So basically, you could have used that setup.
Okay, so we are varying the height and then we are finding the wavelengths for different.
Yeah.
We have done a different
I only saw it once.
Okay, fine.
Thank you.
Since we have 3 minutes remaining, and as per the schedule, we cannot start the review before time. So basically, you get extra time to prepare for the review. We will start after 4 minutes. 3, 2, 1, start.
So first of all, I would like to point out just one thing, so that their presentation will be good. They had sort of unfair time because they had too much material, but they had very little time. So they just skimmed over some sections without even properly explaining the significance of the things they are using. Second of all, I would like to point out some good scientific points, scientific things they have raised in this presentation, the usage of Weber number to justify different conditions or different perceptions of same thing, and they also properly use a proper mathematical framework using Navier-Stokes relation and all the mathematical and calculus to properly develop their whole theory. Now I would like to also point out some shortcomings. They like I mentioned before, they used various relations but did not explain proper significance to it and just skimmed over it by just reading it. Also, they had a very nice attempt on explaining all the proper questions which were given in the initial question. They all explained properly all the relations, all the dependencies of density or shape of orifice and etc. on the actual wave pattern which should be seen. Also, they have done a very good work on the explaining all the limitations which have been pointed out to them in the report, and even they have considered. They have went one step further and also used the damping forces to properly explain, damping forces like viscous forces to properly explain their point in the presentation. I would like to now review a bit on 3D.
1 minute remaining.
Yeah. I would like to just point out that the damper was already added, which was first pointed out by you. But yeah, the good thing is you also pointed out the need of azimuthal harmonic oscillator. So that's a nice thing. Also, you mentioned the use of Bessel functions from the initial paper, and yeah, they should have done that. And finally, just to mention, you critique on the experimental method, but like they have the independence to do anything until it connects to the proper theoretical frameworks. All in all, it was a very good presentation and fairly good critique.
Yes.
Schrödinger's dogs. Are you ready with your presentation? You still have 3 minutes to start. If you want, you can take 3 more minutes, or you can come here. Okay. So 3, 2, 1, start.
So, hello everyone. We're trying to help Bonita with a water bottle and our presentation. This where we model them basically as the 1D bottle fit. So, we basically use a theoretical framework of mostly angular conservation and a 1D model. And in that 1D model, we use like n slices of water where we take the center of masses and in a line, and we basically simulate the physics. For simulation, we use Python, and for experimental observation, we use Capstone to verify what our that is. And we'll also at the conclusion, we'll find the optimal winning strategy for Bonita that will help with the first bottle. So basically, in a fluid water bottle, what happens is when we flip a bottle inside, we after analyzing the movement, we find that for most bottles, the water stays in free fall, and then the bottle comes back and sloshes on it. That decreases the omega of the bottle, and so that it can land properly. So the most basic thing is that the angular momentum of the whole bottle is conserved as a whole, and the variables we're gonna change, the parameters we're gonna change are mostly omega naught and the viscosity of bottle. This is a theoretical. So angular momentum stays constant for the bottle. If for simulation for rigid bodies, this omega is same for liquid fin bottle. Water sloshes outwards during its flight. And the whole thing that drives the movement of the omega changing is basically the centrifugal force. So this is the mass behind it. That's the center of mass of any particle slice. Center of mass position of the whole bottle. You can see we consider center of mass of each of the water particles to calculate that. And the total moment of inertia of the bottle and the whole system combined can be given by that. So that's kind of difficult to understand, and that is basically our model. It's just a stick acting as a bottle, and the bottle has kind of a 2D model so that it can interact with the ground basically. So that stick basically just rotates, and you have n slices on it at different height that acts as water, and then So this is the moment of inertia of the bottle of the bottle about its own center of mass. That is the new shifted center of mass. That is the whole total systems. Total system center of mass is the water column and all its own, and that is the shift. So totally finally we get the moment of inertia. Yes, this. And this you might have recognized this as the inertial frame of motion. We are basically calculating the simulating it with respect to the center of mass of the stick or the bottle. So this is the frame of reference. For the frame of reference, we use this. Here we have centrifugal terms, Euler terms, and it's also we can only simulate like linear viscous drag in this simulation because of limitations which I'll come to later. So the kinetic energy of the water is given by that apoptic potential. This is the Lagrangian equation for solving that equation. Like, and this is like the angular upgrade like each step. From solving that equation, we get this as a position of the ith particle in some t time. You can look at this if you want to, or just like think about it as a stick that's rotating a thing, and the code is doing all the work for us. The same equation, not the same equation. I mean, the same physics. For the simulation parameters, the bottle has a 2D kind of structure, but there's a 1D stick inside it that's like acting as the bottle's like axis for the mass to go in.
Please move a little bit to the left.
So we took 10 power 4 time steps. The total simulation is 0.6 seconds long. I'll show you on the next slide why it's 0.6 seconds long. And water columns and slices and like different heights to account for the like proper mass distribution. And for the code is just numpy arrays for everything. Wall collision, if it's a closed bottle, yeah, this is important. If this is a closed bottle case, if the water goes to the top, then it bounces off with some coefficient of distribution 0.3-ish. And if it's an open bottle, the water should just come out. So that like simulates the open bottle case as well. And for the simplification, we just use an ordinary differential equation instead of using like Navier-Stokes because it's very computational. So like the limitations of this simulation would be like incompressibility is assumed. The water molecules don't actually interact with each other; they just pass through. We could have implemented a like water interacting with each other to get a better thing, but the simulation will have been like n terms, so like 10 power 4 steps into 100 slices. That's a lot more simulating than normal. And water can only be ejected in integer slices of n. You have 100 slices, so it goes up by 1% instead of like continuously, like 0.1, like, over the time, over the course of the model. And we can't simulate sloshing, so it's like the whole principle of the water just coming back. We can't simulate sloshing properly, but the model of 1D surprisingly does approximate that very well. For the it's a fixed rotation axis for the bottle, so like the bottle doesn't move around like left and right; it just rotates around one axis. Because like 2D axis, you can assume. And for linear viscous drag is also another limitation. Only linear viscous drag, and that too with empirical drag. So like the constants aren't correct. You can't just enter any random value to get the correct equation. It's like a range. For the open bottle case, the tip of the boundary condition exceeds, and the like water can be ejected. Mass. For like most of the testing, we found that the initial angular velocity we fixed at 20, and like 20 minutes. For 20 grams per second, and most of it we treated as this. If it's like 20 to 30% of the bottle's filled, then it mostly behaves just like an open bottle. Like the water doesn't like come out. Sorry, closed bottle. The water doesn't come out in the open bottle case. For fluid viscosity and drag, when the drag is increased, then the whole thing starts to act like a solid. Like if the drag is like 1, the maximum, then the whole thing just becomes rigid body motion. That's making sense. For the in our simulations, we found that the fill fraction is mostly best at 20 to 25% for like an ideal bottle flip condition. We didn't actually like calculate how many bottle flips because we cannot do that, but it's like the best case scenario for the omega to change such that the bottle flip happens. So like you need actual skill to bottle flip. Yeah, this is the simulation. Here water mass is 0.3. That is calculated in water, that's the rigid body, and that's the constructive water. And closed body. Okay, this graph is interesting. This gives you all masses. This is a closed body case, that's the open body. 0.6 seconds, 0.6 seconds. You can look at it if you want. Just like, notice how the rigid body is over there, and 0.8 seconds omega kind of behaves weird. You have in the open bottle case, you see that for the 0.1 kg, like you can notice that the water doesn't come out because it goes up and then it comes back up a little bit. And for all of these cases, the water comes out so that like omega will show in the video that how the water comes out, and omega is actually the stop. Yeah. This is the motion of the top of the bottle, cap, and the bottom. Because if a closed bottle, you can observe that this is like the vector representation of that bottle. It's just showing us the stick. And that's like for the open bottle. Observe that for the blue line, that's the 0.1 kg mass. Bottle actually like comes around and fits. For all the other lines, 0.3, 0.5, 0.75, they just stay in the same horizontal. Zoom.
Just mention what the levers are.
This axis is the y-axis for the height, and that's the time. This is which calculating of that's like center of mass. Center of bottle, the top of the cap, and bottom of the bottle. There's solid lines at the top, bottom lines at the bottom. Sorry, dotted lines at the bottom of the cap, of the bottle. For alpha, this is a simulation for alpha. So the more viscous the thing is, the more like a solid it behaves. Next. This is the simulation for the angular velocity with different drag coefficients. Look at that, that's like a rigid body. This green is a lower omega, sorry, a high omega, medium omega, low omega. This is just water. This is closed bottle, and that's for like the open bottle. Open bottle, you can observe, even there, observe that the thing is better, or there's more response. We use a smartphone camera to capture it and analyze it in fast and find out omega. Observe that like the bottle is rotating. This is the mercury. It's like free fall. It just hits the other side of the bottle. Now it's in free fall again, and it stands down. So it basically like cancels out the bottle's angular momentum, and when it slides down, it also cancels the. Okay, that's for the like open bottle case. Observe that. Yeah, see that all the angular momentum gets cancelled. That's like the movement showing that.
I think after that angle it will not be
Okay,
considered.
that's right.
Let's show this. It's kind of
Please stop. Virtual Gluon Goons. Ready? When I say start, then start. 3, 2, 1, start.
First, I would like to recognize their presentation. It was well articulated and it had lots of mathematics to justify their open bottom and closed bottom case. So the main issues that I would like to point out is their optimal fill fractions which were recommended. They vary throughout the presentation. At one point it suggested 20 to 25%. In the conclusion it suggested 20 to 30%. And another point that I would like to
make is they assumed alpha to be constant. It depends on velocity also. And they assume that the bottle boundary to be inelastic, which is not.
Take your time.
And then 1D, as they pointed out, the 1D analytical model is a bit simplified and it doesn't account the sloshing effects of the water. And they have assumed that water to be an uniform column in their 1D analytical model, which contradicts with their next assumption in their n slices model, where water is not where it contradicts that water is a uniform column. And one more point that I would like to make is, in the open bottle case where water is greater than 50%, they suggested that there should be higher omega naught to avoid water leakage. But when omega naught is increased, there will be more centrifugal pressure, which increases the chances of water escape from the bottle. It should have been less.
Wrong brothers, you have 5 minutes before the review starts. 3, 2, 1, start.
So I'm on behalf of Gluon Brothers here, and I'm criticizing. So firstly, I would like to appreciate a few points about the experiment. Firstly, I would like to appreciate the choice of the model that they used, the M-splice model, so that it perfectly encapsulates how the bouncing around will happen, but it also reduces the amount of computational effort in the simulations that will be there. But I would also like to say that they acknowledge the limitations of their model. They mentioned that a 2D fluid model, like to say a 3D model, they had tried, but then the blender simulation of that was not feasible. They acknowledge the lack of the linear drag. So they acknowledge that they had used a linear drag model when they would have used more complicated models instead, and the incompressibility and the fixed axis that they had assumed. I would like to also appreciate the new factors that were introduced in the presentation. The Lagrangian was introduced as a possible method to solve the system instead of methods. New graphs were introduced in section 3.1 and 3.2, which pointed out the percentages of water and how the final experimental results will change with that. And also, graphs with impact of alpha on the angular velocities were introduced, which was not there in the original document. But the graphs in section 3.1 and 3.2, as pointed out by the conveners, were not really visible, and hence we couldn't gain much information during the presentation itself. Yes, so some things about the experimental techniques. Again, first I'd like to go to the criticisms that were provided. So firstly, the inconsistent optimal percentages that were given were acknowledged, and that was acknowledged, and that was one major factor. Also, there was no theoretical basis that was given for that optimal basis. That was not provided. That was not sent by the agencies. Also, the high omega theta criticism. So in the high omega for the open bottle criticism was perfectly valid, but they should have also attacked the thought process of the presenters, where a high omega can lead to a decent omega when it is ending, which and the stall in omega would not happen. So that should have been pointed out. The coefficient of substitution was taken in the by the presenters, so the inelastic collision system was not valid. And yes. I think yes, they could have pointed out on the lack of certain experimental techniques. The bottle should have been more simpler, and the graph of omega was fluctuating a lot. That could have been pointed out in the techniques.
We have a 10-minute buffer period, after which Uniqueass Theorem will present. Three, two, one, start.
Okay, so this is the problem statement. So the abstract of the problem is that whenever you pour liquid or fluid from glass or any orifice, basically, if you're non-opening or circular opening, the jet that is formed is like chain-like structure we observed. So basically, that depends upon various parameters. And so when a liquid such as water is poured from a glass bucket to the structure appears alternating wide and narrow region along this, so the water is going the pattern is stationary. This phenomenon arises from the interaction of surface tension and fluid inertia and geometry of the object. These patterns can be interpreted as deadening waves, basically nodes and anti-nodes. As the liquid falls or travels through space, its cross-section oscillates between different shapes, often switching between two perpendicular elliptical orientations. So the physical mechanism that is being implemented is the wave pattern originates from the breaking of circular symmetry when the fluid exits at a nozzle or flowing surface. And when the opening is circular, there is no, you can say, restoring force. That is the surface tension. When the opening is non-circular, the surface tension acts as the restoring force, which basically squeezes the jet and makes the oscillations. And so these are the theory, the formula that we are using to explain why these are happening. Okay, so basically, okay, so if I say this is the opening, this is the elliptical orifice. So here you can see that the radius of curvature is larger and here is smaller. So the force due to the pressure difference here is smaller and here is larger. So the jet that is being formed will squeeze, and when the orifice ultimately forms circular, due to fluid inertia, it will squeeze further and ultimately will form the elliptical shape similar to this but with different orientation, like this perpendicular. And the squeeziness will continue and will eventually make oscillations. And so this is the experiment that we have done. So basically, a circular orifice will form like this, and the elliptical orifice will cease like this. Basically, what we are seeing here is so now you can see not yet the wavelength here. The wavelength of the jet is smaller here, and there it's larger. Okay. And this is the simulation that we have done using Python. So basically, what we have done is we have based the wavelength and we change the parameter that it is dependent upon. So we change the velocity. We can see the the shape of the jet being changing. So yeah, in the mathematical description. So the analysis that is done by the Lord really, we get that the wavelength of those jets is dependent. It's like this. So Rod Larry done the linear approximation, but further than needs for further extrapolating that theory into non-linear fluid dynamics. So we get complex shapes and all, and ultimately we get the wavelength just like this. So wavelength is dependent on these parameters. So, like as we saw that the wavelength is dependent on velocity, initial velocity, radius of the orifice, and density and surface tension. So, the influence of velocity and flow rate. So, like it's the most visible parameter affecting pattern. When the fluid travels faster, each oscillation of the cross section is stretched over a greater physical distance. So, as a result, increasing flow rate causes the wavelength of the pattern to increase. So, yeah. And here we can see that high pressure, as in more initial velocity, the wavelength is large, and in smaller it's small. And the effect of nozzle geometry is the orifice. So the opening is strongly elliptical or irregular. The initial distortion of the jet is much larger. Like if you can say like an ellipse has eccentricity, right? So if the ellipse has more eccentricity, the non-cylindrical characteristics of the wave will not be there. So yeah, and the influence on density of surface tension. So basically, this is the Weber number. So it's just inertial term upon surface tension. So as I said, that the fluid has some inertia when due to pressure difference, it moves, so it has inertia. So that inertia is dependent on like this. So surface tension exists in restoring force that drives the oscillation. So the relative importance of the inertia is often summarized by the Weber number. Yes. So this is the formula. So the conclusions that we can make is, as the density of the fluid increases, the wavelength also increases. And the same can be said for the radius of the orifice and the velocity. And the initial perturbation amplitude or orifice of the elliptic orifice provides non-cylindrical characteristics of the wave that is formed. So, therefore, we can say that we verified the theoretical aspects information of wave patterns of the jets. Yeah. So now the answer to the problem statement, the nodes and what we think is that the nodes and antinodes that are Kinney observed may not be correct terms to use there. Kinney might have observed these patterns to one of the Fourmion waves and wasn't able to see the other wave plane and stating them as nodes and antinodes. So yeah. And yes, we can generate many interesting shapes. Like if we make the orifice some sort of 3D and twisted, we can see a helical pattern.
Exam leaders, you have 4 minutes for time.
wrong with the stream and we are criticizing the work of the Uniqueass Theorem on problem 2. So firstly, on the report, we found that the impact of viscosity, the impact that viscosity had on the fluid patterns was not studied, and it should have been mentioned and studied better. There was no proper mathematical basis given in the report, like derivation of formulas, but since it was given in the presentation, that's a good point. We have improved. The results that they had shown was purely qualitative in nature. We felt that it should have been more quantitative. They could have added more numerical results, maybe analyzed the photographs that they've taken with Pascal to figure out what distance and what amplitude they had gotten. There was no stability criteria mentioned, and it should have been simulated at least or experimentally tested. The amplitude of the standing waves could depend upon the z and on time, and due to damping factors, and this was not studied or omitted. And one thing was that how they prepared the orifice for their experimental testing. We felt that it was not very well explained as how they maintained the accuracy of the shape and stuff like that. For the presentation, we found that they did not mention a phenomenon that could occur with even elliptical orifices, where you get slightly concave shapes at the antilodes, slight concavity at the antilodes. Complex shapes were just creating complex shapes were just mentioned. They could have tested it experimentally or verified it experimentally as to what orifice creates that. In regards to this, it was mentioned that due to non-linear factors, they generated complex shapes to be generated, but linearity is not very clearly explained. Like in what variable it is linear, and laminar flow was during the whole process was assumed, but it was not stated anywhere. So these were the points that we have found again. Thank you.
Fourmions, 3 minutes. 3, 2, 1, start.
Hello. So the presenters did a good job in explaining the pattern formation in falling liquid jets. They explained how non-circular orifice creates a distortion, and the surface here tries to restore the circular shape, but while doing so, the inertia overshoots it, and this creates an oscillation. They correctly identified the parameters like velocity, density, surface tension, and other geometry which affect this phenomenon. They also supported it with 2 experimental gigs of different orifice geometries and different flow rates. Weber number was also correctly introduced, and they also gave a 3D simulation which produced a result of wavelength of around 21.8 centimeters. The Critic team was also very good in addressing good points. They correctly identified that they did not highlight how amplitude depends on Zn or T. Also, they missed out on the ensemble number concept, which we not discussed. Non-linear effects are also mentioned but not followed through. But one thing of both the presentation and the Critic missed is that the n equal to 0 case and the cross-section oscillations are 2 completely different things, and the mathematical background behind it was not clearly done. One thing I would like the jury to notice is the simulation result of wavelength that was produced of 21.38 centimeter. They did not check if it was consistent with the analytical prediction or not. So I would like the jury to look on it. Overall, the presentation was good and the critic was to the point. They made the correct observations, but they highlighted the need of explaining the process of preparation of orifice, which I don't think is a really important point to this problem of analyzing the and mathematics behind it. Thank you.
Two, one, start.
Good afternoon, everyone. Today our team will be presenting a solution on the third problem which is on the dynamics of body flip. So firstly, we'll explain the problem statement.
A bit louder.
Firstly, we'll explain the problem statement. So in this problem, we need to find the optimum conditions of the body flip by varying various conditions like the fill fraction, initial angular velocity, the release angle, and the fluid properties. So challenges in this problem are if we are taking a rigid body and it has constant angular momentum and the angular velocity is not changing, it's very hard for the flip to be successful because the angular velocity is not decreasing. This relies on dynamic mass redistribution, which means as you flip the body, mass redistributes, which lowers the angular velocity and helps in the flip to be successful. The challenge in solving this problem is to accurately solve this, we need to simulate using Navier-Stokes equation, which is computationally highly inefficient. So the solution to this problem is using a simpler mechanical model to reduce the complexities. So these are our assumptions to perfectly, not perfectly, but to closely represent a body. We are assuming it to be a perfect cylinder with these complexities, whose height is 22 centimeters, radius is 3.5 centimeters, mass is 25 grams. And we are also assuming the wobbling to be negligible, meaning the motion is almost stable. And the condition for landing is that if the angle at which body lands, if it is greater than 1.5 times the critical angle, which is the tan inverse of R by Z, if it is within that, you can considering the body flip to be successful. I'll elaborate more on it, but if the angle is too low, then body won't be able to stand upright. So we are putting this limit. Also, we are assuming the coefficient of restitution to be 0.1. Keeping it low because as the body is flipping, the water inside, as it is flipping, and the bottle is about to bounce due to the impact, the water pushes it down, and hence it isn't able to rise high. Hence, the coefficient of restitution is low. We can call this water hammer effect as the energy is getting lost. And we are also assuming high static friction so that there is no slipping upon. And here are some more assumptions. Firstly, we are assuming the flow will be irrotational, meaning the curl will be zero. Using this, we can say that del square pi scalar potential for the velocity vector that will be zero. Also, we are assuming viscosity to be very low and fluid to be incompressible. We are also neglecting the aerodynamic forces as their magnitude is very low compared to gravity. In our experiment, we are using three models, which are the sliding plug model, pendulum model, and the ball model. In the sliding plug model, we are assuming the model to be a point mass, which is sliding in one dimension. This assumption is very good for low angular velocities. And our second assumption, which is for medium angular velocities, is the pendulum model, in which they have a fixed mass and a pendulum mass. This is able to simulate the sloshing, the slight sloshing, the fluid motion of the water very well. And for higher angular velocities, we are using the tennis ball model, which means there's a fixed wall or mass at the bottom and a movable mass at the top. So they are trying to see the water splitting into parts. We can justify this using rotational fluid number, which is R omega naught squared by G. If this value is very low, then use the sliding plug model. If this is in medium range, the pendulum model. So I use the telescope model. These are the ranges of the angular velocities. So now getting on the equations part, we can for all three models, this will remain the same, meaning the kinetic energy of the bottle and the potential energy of the empty bottle. This will remain the same and it's given by these formulas. And we are defining x and y to be position of the bottle center points, and alpha will be the angle made by the bottle's axis to the x-axis. So this is the equations part for the sliding plug model. We can very easily find the position of the mass as moving in one dimension, and it is given by that. S is the distance of the body mass from the center. So this is the equation which you get upon applying the Euler-Lagrange equation, and this represents minus C is what represents the frictional drag. Now moving on the pendulum model, you can see that you get the solution by solving the Laplace equation, that is for pi equals 0. The solution are the Bessel functions. Main point is that when you solve the Bessel function, we just take the primary value as that is what contributes most of the energy, around 95%. So we neglecting the higher values. We are taking these values from the paper by NASA, which we have cited in our report. And yeah, these are the we get this mass matrix in this equation. M to the naught is a function of force. And by solving this, like taking the M inverse that side, we can find like Q W naught. This is the Lagrangian for the small model. So we obtained this graph by plotting the number of successful initials we have tried, which are the initial angular velocity and the angle of release versus the fill fraction. Now we can clearly see that there is a peak at around 0.35. There's also some discrepancies for lower fill fractions. Now this is happening because for lower fill fractions, our models are not very appropriate. For example, in the tennis ball model, for low fill fractions, there's not enough water for like two mass weights separated. So hence we are getting discrepancies over here. But we can clearly see the peak to be at around 0.35, which is the optimal fill fraction. And this is the 2D phase space for fill fraction equal to 0.35. We are reading omega and theta. So like blue areas here represent successful model flips, and blank area means the model flip is not successful. We can see that success appears in bands, and as we get to the higher angular velocities, bands are getting closer. They look joined because our resolution was low due to we didn't keep very high resolution. So like we can also see that for close angular velocities, as the angle of release increases, the angle of initial angular velocity is decreasing because you have to go less angle. So angular velocity is decreasing. This is 3D phase space. And then we plotted the number of successful initials, which are the initial angular velocity and the release angle, versus the fluid density. We can see it peaks at around 1000. Now this is because of the dimensions of our bottle. For heavy fluids, when you flip it, the energy is so high that it is not stable upon the impact. Hence, it's difficult for the bottle to flip. And for low density fluids, what happens is that the center of mass is not able to shift effectively because the mass is low, and hence the angular velocity is not able to get low enough when the mass gets redistributed. Hence, the success rate is low. This is the 3D phase space for this. And now
That's 3 minutes remaining.
Yeah. Now moving on to open bottle dynamics, we can see we have used a simple model. Like the rate of mass rejection is minus rho A P eject. And this is the graph which we have plotted for fraction equal to 0.35 and angle as pi by 4. So you can see the mass dependence for different ranges of velocities, high, medium, and low. And this is the graph which we get for number of successful initial conditions versus the fill fraction. This is at around 0.32. We're getting a lower fill fraction compared to the closed bottle because let's say if the mass of water fluid is higher in this, so fluid is closer to the cap, and hence it is more likely for it to get out and destabilize the fluid. This is the 2D phase space for fill fraction to 0.32. We can see again the success will appear in bands. This is the 3D phase space.
This is what is used for our experiment. What we did was we varied the fill fraction by 5% and we obtained sort of a bell curve. We did 20 flips for each and marked how many times were successful. So this was the graph we obtained. This was the closed wall and this is for open wall. Now moving on to our limitations and conclusions. So we find that the optimum strategy is fill fraction to 0.35 for best results, and the density should be around 1000 kilograms per meter cube. And for an open bottle, the fizz fraction is nearly 25 to 30%. These are some videos we captured for different stages of velocity. This is for blue angular velocity. We can see that the mass is not separating.
1 minute remaining.
This is for medium range velocity. You can see it's not separating into parts, but we can see motion distortion in the surface. And for high angular velocities, we can see it's separating into parts. So now moving on to some gaps which we are addressing. So firstly, we might think why are not experimentally predicted constants. So they have used the result from the NASA report. Used it. Now, why are we using the three models using closed? We're using closed model also for the open model. The answer is that the models do not change as it's just the mass which is ejecting and the forces which are acting they are the same. So we can use the same models. So why are we using flip of non-symmetric bottles and justifying it for symmetric bottles? So real world bottles they have complex geometry, not complex.
Your time is up. Okay.
The fine man, you have around 3 minutes, then you can start.
3, 2, 1, start.
Yeah, so about your data, we have read the paper, and there are a few points which I would like to critique and I'll divide them into 4 sections. Number 1 is the assumptions, number 2 the model, number 3 the simulations, and number 4 is how you have related the theoretical incorporation into the simulations versus your experimental results. Firstly, the assumptions. There are some assumptions which are like pretty fine and reasonable. I have slight doubts with like 2 assumptions. Number 1, you said that for it to after landing, the theta has to be greater than 1.5 times some theta limit. But you haven't really provided a theoretical or mathematical or intuitive explanation as to why you have taken the 1.5 theta. Because like by that logic it would be anything like 1 or 2 or something like that. So you haven't really provided justification for that. And secondly, you have made another assumption that after landing, the rotational kinetic energy has to be lesser than the peak potential energy which it will attain at the top. But by that logic, when it reaches the top, it won't be able to exactly reach the top, it will fall back. Right? Like if you assume that the kinetic energy transforms into a potential energy, and if you assume it is lesser than the peak potential energy which it has to attain, it will fall. So I don't know how exactly you incorporated that into your simulation. So that seems a bit problematic. Apart from that, the remaining assumptions are pretty linear. Secondly, the models. Yeah, I see you have included 3 models for different omega ranges. Now there is one slight problem. Like in your paper, you didn't exactly include omegas, but here you included, so that is fine. But these models, they aren't exactly continuous over the transition phases, right? And since the velocities or angular velocities which you have used in the model, they pretty much cover the entire range. How do you justify what form the liquid takes when, let's say, it is transitioning from the slush model to to the two-ball model because it's not a continuous transition. No, in one you're assuming the liquid has totally separated into two at the two ends, and in the other, like around 25 or something, you're assuming that it's sloshed together as a pendulum attached to a fixed mass, right? So how exactly does the fluid behave over this transition? Because it can be very important. The velocities which you got, they are like pretty much in that range of transition. So that is a problem. And secondly, in your paper, the first model for small omega and the third model for large omega, they are pretty much intuitive and reasonable. The second one, it's a bit unintuitive and you haven't really provided an explanation for why you have assumed it as two masses. The mass of the fluid separated into two masses, one fixed at a certain distance and the other fixed at a certain distance and a certain angle, right? Which is oscillating. You haven't really provided a justification as to why that model holds true. The first and the third models are pretty justifiable, but the second model just feels a bit unintuitive. And secondly, it would have been good if you provided a picture because there are too many constants which you are using and you could have provided a small picture in your paper. That's it about the models which you have used, and in your paper you didn't include the slosh why you have considered first fundamental on all, but here you have included such. Thirdly, about the simulations. Your simulations are pretty good. If I see it as a whole, it's pretty diverse and it incorporates all the factors which you were supposed to incorporate. There are some problems, technical problems in your simulations, in the first one regarding the fill fraction and the success rate, you haven't exactly specified what you have taken as the initial angle and the initial angular velocity of flow, because it can mean two things. Either you have taken them to be the optimal conditions or you have taken it to be random so that you get an average value over the range which you are doing. So you haven't exactly specified the simulations for part there. And apart from that, once you have got apart from that, you have got f is 0.35, you assume that and you proceed on to the next parameter. That's pretty good. You optimize one parameter and given that you are optimizing the next parameter, that is pretty good. And next, if we come to the open bottle, there's one major issue here because you haven't exactly specified the area of the orifice of the open end which you are taking. Because that is a huge factor of at what condition the water will come out and how much water will come out. That exactly depends on the area of orifice which you are taking. Suppose it's a very small area of the open end like a bottle, or is it the entire end is open? So you haven't exactly specified that. And I don't even that you haven't specified that, I don't exactly know what those graphs about the volume of liquid in the bottle exactly mean, because where exactly is the orifice am I supposed to assume? So that is a major problem in the open model. And secondly, in the open model, you have obtained the F, the fill fraction optimal experimentally to be 25%. But in theory, it's around 32%, which is much closer to the 35% which you had got for the closed model. So that, and in your paper, you specify that as a very good agreement, but it's not a very good agreement. You're experimentally getting 25% for open and 35% for closed, and theoretically your simulation wise you're getting 35% for closed, which is agreed. But you're getting 32% for open, which is a very huge deviation from the model, right? That is a problem, and you haven't exactly addressed this error in your conclusion because it's a very huge error. And because you have this huge problem of the area of the orifice not being specified, that might be a problem, a problem causing factor, right? So that is one problem. And in conclusion, your report was pretty good, except the points which I mentioned, and you could have provided a conclusion as to what exactly this Bonita guy has to do to optimize the bottle flow, right? You specify 35%
1 minute.
Yeah. You specify 35% in the bottle, you specify water has to be taken, but what exactly is the guy, what exactly does the guy have to do? He has to go and throw the bottle. No, everyone has a bottle with 35% liquid in it. What exactly does he have to do to attain that high success rate? You did specify it has to be very high angular velocity, fine, but how high? And in what range he has to throw? Assuming it's 1 meter above, which you have assumed in the assumption that you are throwing it, given there's a problem of your coefficient of restitution, and the fact that your landing parameters, landing assumptions are not exactly working, and plus this guy has to do with an open bottle, I think the success rates will be much lower than what you have calculated, which are already pretty low because of your open orifice assumption. So in conclusion, closed bottle model was pretty good, open bottle has slight errors which could have been addressed. That's it.
Get your gluons, be ready for the review section. You have 3 minutes for now.
Ready?
We have 3 minutes.
2, 1, start.
So the presentation was pretty good. They used a hybrid model which allowed them to sweep larger parameters. Like the sliding models was low omega, fixed mass and pendulum models for intermediate omegas, and two-pole model for the high omegas. Also, they include dissipation function and use of simple Euler-Lagrange equations to simulate their work, which was pretty good. They also made fundamental assumptions to simplify the complex dynamics, like the bottle geometry, planar motion, and landing criteria using the water hammer effect. Also, the surface friction is assumed to be high enough to prevent the pivot point from sliding from the impact. Also, they were able to quantify the fill fractions ratio, which was quite notable. Also, they acknowledge the oversimplified assumption which they made, due to which they can't accurately model heavy sloshing and vorticity of fluid and the density impacts. About the critic mentioned that they were not able to explain how the models transition, how the liquid behaved between the model transitions, and also they questioned about the second model. Also, they mentioned about the technical issues which were there, and also how the simulation data and the experimental data vary.
Now, 3, 2, 1, start.
Our in the wrong reverse is going to present the first problem of EYP, a new problem. In this, we optimize the paper plane for range as well as load carrying capacity. Now, what are the abbreviations? First, CD is drag coefficient, CL is the lift coefficient. This will come up later. L cap is the direction of lift. This is perpendicular to the plane itself, not necessarily velocity, because of angular. S is the wing area. Rho is the density of air. Alpha is the angle of attack as mentioned. Cm is the pitching moment. Now, this is similar to the distance between center of pressure and center of gravity. Center of pressure is where all the aerodynamic forces can be assumed to act. RE is the ready policy. Sorry. So, as mentioned before, we are optimizing it for range and load capacity. We are optimizing for range and load carrying capacity. The parameters that we have used are the aspect ratio, the folding. We have 4 possible foldings, out of which one is original. And other than that, we have also varied the load and angle of launch. Angle of launch was kept approximately constant in our testing, but in simulation, we have varied it from 0.5 to 1 or 0.6 to 1. Now, why is this non-trivial? It's because drag and lift are velocity dependent, since we have used dynamic pressure. And the load also can change the center of mass, so that was in our testing rather than our simulation. That is a more minor effect, though it also affects drag, lift, and moment of inertia. Here are our paper planes. We used the Suzanne, which was the world record for distance in 2012. The Nighthawk, it flies far, it's from foldable flight. The Firefly, the current world record as of 2026, which was achieved in December 2025. And our original plane, we call it the Super Duck. Sorry about that. Technical issues.
Okay, pause the time. We should consider
This should. So, let's go over an overview of the paper plane itself. Now, the Reynolds number based on the viscosity and density of air, as well as the size of the paper plane and the velocity of light, comes around 10 power 5. It's on the order 0.5 to 1 into 10 power 5. Now, this matters because turbulence is important at this ratio. We have approximated it with laminar effects, but we do need to include turbulence. Now, most paper planes have a drop delta wing design. this matters for center of pressure, center of mass. The lift to drag ratio is around 5, which is quite good. The model assumes laminar flow of air as mentioned before. Since the rotation of the Earth is extremely slow and during the Earth frame, it assumes a linear frame of reference. Despite the goal of this to get paper team off of plateauing, we assume constant gravity since we do not actually get such high ranges and heights. And we assume that the plane flies straight, essentially motion in one plane perpendicular to the ground. Now, look at the center of mass dynamics. Now, the center of mass observations depend on gravity, lift, and drag. Lift and drag depend on the dynamic pressure. Now, I'll show you a free body diagram. Say if you have a center of mass here, gravity acts downward, and say velocity. Velocity is here, and this is our angle of action. Now, drag acts anti-parallel to the velocity. And lift does not act perpendicular to the velocity, it acts perpendicular to the plane. And the actual values or expansions are given over there. Now, CD and CL may vary over the velocity as well as angle of attack. CL depends on the angle of attack, which varies sinusoidally. Okay, we don't have that right now, but as per the Faraday algebra, it varies sinusoidally. It also depends on aeroelastic washout, which is where the angle of attack of the wing changes over the span. Now, CD changes based on CL. This is lift-induced drag. And independently, it varies based on angle of attack, that is the stalling behavior. Now, theoretically, stalling should come under CL, but when we decompose it into the X and Y components, that is when we are using Cartesian coordinates, it does not really matter for the simulation where we put it. And it also depends on the plane model usage, parasitic drag. We assume that each piece of paper is a flat plate and we use drag accordingly. Now let's look at torques. Now the torque is primarily from the lift. Now that's the drag is anti-parallel to the velocity and the angle of attack alpha is generally quite small. This we found from the simulation. So we are considering torque to be only due to lift. Now in an actual paper plane, our center of pressure and center of gravity need not be at the same place. So lift can create a torque that's this in either of these directions, depending on Cm, that's the pitching moment. Now we cannot directly use the center of mass and center of pressure, since the center of pressure changes and the pressure is not constant over the entire wing area, whereas we have approximated that. So which is why we have a variable Cm factor. Now let's come to stability. Now stability is not captured in the equations of motion. That's due to our straight path assumption. We are taking a perturbative approximation to that. So centerfold, that is the fuselage of the paper plane, increases yaw stability. Now if you just look at the moment of inertia along that axis, that is reduced. However, if you try to yaw a plane with the fuselage, it's going to push against the air, so that's going to make it harder. Now we also have a dihedral angle for the wings. Essentially, the wings are tilted upwards.
Against remaining
5 minutes, okay. So the vertical component of lift in the direction of roll is increased, and the vertical component of lift from the other wing is reduced. This stabilizes. Now these are the equations here. This is just elementary trigonometry as mentioned here. Now coming to the simulation, we've used the solve IVP or solve initial value problem solver from Cycle. Now this is an adaptive solver. The step size varies based on the derivatives that is available. If the rate of change is smaller, it selects the larger step size for efficiency. Now the method that we used is the Radau method. This is an implicit RK method. Now it has a certain stability criterion called A stability that minimizes energy errors. Now, just an overview of what the code does. initially we defined global variables for physical constants and temporary variables. So, for example, the gravitational acceleration g or the air density would be defined there, as well as placeholder wing area that scales with the aspect ratio. Now we have a class paper plane, so this is to set the drag coefficient, pitching moment, and how they vary. Lift and drag coefficients and aeroelastic effects, how the aeroelastic effects affect them. These are in a get forces function, which then goes into a derivatives function for the time steps. Now we determine velocity and acceleration based on that. We break the loop of flight once the plane hits the ground. Now aspect ratio, which is referred to by any of those names in the code, is we have an unconventional definition here that's more of the colloquial definition. That is the maximum caught by total span. That's not based on the wing area. Now this is just a sample trajectory. You can see it's called a phugoid curve or phugoid oscillation. Now since we don't have thrust, and due to the higher drag coefficient, we can see only one period of oscillation here, and it's moving down due to the lack of thrust. Now here this is for our optimization. This is aspect ratio. Now we don't know that aspect ratio, mass, and flowing angle will affect the range independently. So we combined all of them into a single graph per plane. That's the range, and we can see that aspect ratio on 1 to 1.5 is good for Suzanne, and it quite rapidly reduces afterwards. And it's predicted that mass increases the range, which we found to be true mostly for the dart-like planes, not for Suzanne or fireflies. It's a similar graph for the firefly. Super dart is our original. Now the planes were thrown by hand, and we used the 5-meter measuring tape to measure those. A video was taken using a phone and a tripod, and we used the video analysis feature of Pasco capstone to find the initial velocity as well as the launch angle. Now for load, since we could not vary the GSM of the paper, we had to use a uniform paper. We used staples, each of them are on 50 milligrams, in batches of 20, 40, and 60, so 1, 2, and 3 grams. So our limitations were that we could not keep the angle of launch constant since it was done by hand. And so there's human error in the range as well due to launch and measurement. And it's very highly sensitive to asymmetry. So even without any wind, we found that most of our planes tended to yaw left. This is because of a slightly curved fuselage in our fold. So this was an issue because our trajectory was not in one plane. And any wind will also affect the range of the plane. Aspect ratio here can refer to either the paper or the aeroplane inconsistently.
1 minute remaining.
Now, for our results, the unloaded Suzanne had the maximum range, and we, as mentioned before, the dart-like planes benefit from load. Now, our original plane, the Super Dart, with an A4 aspect ratio, had the highest range at 2 gram load. So, we did find that we optimized with our own food. Here's our experimental data. And the Firefly doesn't have data for aspect ratio since it requires precise length measurements which you could not translate to other aspect ratios. Nighthawk is just missing data. Again, missing data for Firefly, but as you can see that the highest loaded range is at 2 grams for the Super Dam. For future work, we have to look at static control surfaces to correct for the natural tendency to roll or rock. We have to consider turbulent flow and ground effect. So, since our Reynolds number is high, we should not be neglecting that.
Time up.
Thank you.
One small clarification. For simulating different kinds of planes, did you just change the aspect ratio or were there any other parameters changed?
We changed the parasitic drag coefficient and the pitching moment and its variation based on the pressure, that is velocity and angle of attack.
Okay.
So those are empirically.
Okay.
You remarked something about the energy constant. What was that?
So many methods such as will not conserve energy.
Schrodinger's dogs be ready within 2 minutes.
So what did you do?
So the ladder method minimizes those due to a certain condition called A stability, whereas decays are certain decays are below A stability. I'm not sure about the details of that, but as I understand, certain decays in differential equations are preserved. That does not eliminate the energy issue like the velocity value type methods, but it does reduce.
Does it approximately conserve it?
Approximately, yes.
So, are you ready? 3, 2, 1, start.
Okay, so I'll be critiquing the paper plane model. So here, one thing I would like to point out is that there was very little mathematical framework that was explained in the paper. But in the presentation here, they included some mathematical framework, but it would have been better if they added much more to the scope. And also, there were many new terms in the paper, which would have been, it is very vaguely mentioned in it, and it would have been better if they actually gave a very small explanation for what those terms are. And another thing I would like to say was the experimental data and the simulation data, I felt that it wasn't properly compared, and also there was, also in the report, they mentioned about 4 different things, but in the conclusions, the inferences were made only for 2, and for the other 2, there weren't many inferences that they drew from the thing. But yeah, I think they corrected that in the presentation. And also for also in the range calculation, they had got like a 50% error. Like they got half the value of what it should have been from the experimental part, for which they mentioned that is probably due to the underestimation of the CD value, which I think they could have run the simulations taking from the experimental data. They could have back calculated the CD value and tried running the simulations again, and could have gotten better graphs for that. And also they also mentioned that the Reynolds number is very high, that is like 10 power 5, which lies in the turbulence range, but they have taken the assumption that it is the laminar flow, which I feel that assumption leads to a lot of error. And other than that, the other assumptions are pretty fine. And also, they took 4 different planes. I think if the sampling rate was more, that is taken more number of planes, and also like if they have taken more number of models for the planes, they could have given more clarity on what is the best plane for the optimal structure.
Now projectile dysfunction. Please be ready with your review section.
They have time.
So you can take around 3 minutes.
Ready? 3, 2, 1, start.
So, firstly, I'll be presenting a review of the presentation as given by the team Long Brothers on the airplane problem. So, they started by putting forth their problem statement very clearly, and on one slide they defined the parameters also very clearly, like what parameters are they taking, what are they actually varying, and the setup was also very well explained. For example, they showed the images of all the planes they have used, and even later in the presentation they showed that actually how they've recorded the flights and how they varied the loads by using stapler pins. And the constraints were also properly stated. For example, the Reynolds number regime they are working, so they stated they are working at a Reynolds number of the order of 10 to 5. And they also stated in the constraints that the lift coefficient varies sinusoidally with the angle of rotation. And then they proceeded by providing a scientific description of the model on the board. So that description was actually quite complete and thorough. Now coming to the simulation part, so they very clearly explained the computation part of the simulation, how they've computed and how they've solved the differential equation in the code by using the function of sci-fi. And the theoretical graph they've also shown, and they provided the 3D phase space, which was actually quite nice. They could have provided more graphs of the data, like they could have chosen different axes to show the data bit, but they explained the 3D phase space plot quite well.
Now the final results of the experiment, they were not very expansively stated, and the inference was actually final inference that was not very well provided, and so the inference was not very well drawn. And but the future work that the future work they proposed after that was very nice. They included a lot of improvements that they could have done, and also the comparison of the simulation and the experimental data, that was a little less. But yes, now I'll be reviewing the critique as provided by Schrödinger's law. So they said that the mathematical framework was a little less. Yes, this is a little justified. They could have provided more mathematical framework. And they also said that the experimental and simulation data was not very well compared. That was actually done to some extent, but yeah, it could have been more. And they also gave a very good constructive feedback that the accuracy of the range can be improved, and they suggested how it can be improved by back calculating the drag coefficient values. So that was a very nice addition by them. And they also mentioned that the Reynolds number regime was very high that they were working with. So yeah, that is also, they have actually used a turbulent flow.
Time up.
Yeah.
Thank you.
Gluon Goons, be ready for your presentation. And starts 3, 2, 1, start.
Presenting, we did our research on the physics of a falling fluid stream, liquid stream, and here we are actually studying the common life phenomenon that there is a common observation that there are nodes and antinodes formed when pouring water and stuff, pouring water or other liquids. But here we qualitatively discuss how these are exactly found and what effect other parameters have on this, like flow rate and size of orifice and shape of it. In the end, we also say why the use of the term nodes and antinodes is not entirely correct here. And so, for the theoretical framework, we explain the formation and continuation of this patterns using the theory of coercive and adhesive forces. So we propose that when initially we are starting to pour the liquid, there's no coercive forces, there's no unequal coercive forces acting on it that will reduce the shape size of the stream, and only the adhesive forces act, which create a separation that is visible here at the top. There's a separation at the lip. So due to those adhesive forces, it gets it is laterally stretched out, and while going down, when since the number of particles is increasing, the coercive forces increase. So due to that increase, the coercive forces then dominate, and the thinning happens, and the antinode is created, and node is created. And then these nodes and antinodes are further enhanced by by Young's Laplace equation, which basically deals with the pressure differences. The equation is, as you can see, inversely proportional to the radius of curvature as freshmen. Right? So at the nodes, the radius of curvature is larger. So that's why larger as compared to at the antinode. Sorry, at the antinode, the radius of curvature is larger. So that's why the pressure there is lower, and hence the water flows from higher pressure to lower pressure, and the nodes become more thin, and the antinodes become thicker. So the pattern eventually increases the definition of the pattern, and this pattern eventually continues down the stream due to initially it's formed due to the coercive and adhesive forces, and after that it continues due to the inertia of the water stream that it has already gained while going down, and the coercive forces which still act to reduce the size of the fluid stream. This, as you can see, is the explanation photo of the base case that we did. Here the antinodes and nodes are clearly visible, and 2 or 3. Next, we did the experiments for different parameters, and then we also explained them simultaneously. So while in rate of flow, we observed that by increasing at very low rates of flow, there was only dripping, and after that, when at a certain point, the formation of pattern starts, and increasing the rate of flow thereafter increases the wavelength, and eventually there is this turbulence. This can be explained. We try to explain this using Bernoulli's equation and Laplace equation. So we state that the increase in flow rate leads to an increase in average velocity, and therefore by Bernoulli's equation we can say that the pressure is reducing, and Young's Laplace equation, since the pressure is inversely proportional to radius, we can say that the radius of curvature is increasing, and increasing the radius of curvature leads to a decrease in the amplitude at that point, and in the basically the thinning at antinodes happens due to reduction in increase in radius of curvature. Hence the number of particles at that point decreases, and the coercive forces decreases. Therefore, it takes more, and since coercive forces are responsible for the thinning from antinodes to nodes, the time taken increases, and due to reduction of force, and therefore the wavelength also increases. This is at a very low flow rate. We can see that it's just flipping, and that from a moderate flow rate to a relatively higher flow rate, the wavelength increases. And we then did the experiment for different shapes of orifice. So for a perfectly circular orifice, there were no nodes and antinodes formed. I guess we explained this using the theory that we've already used, because there we say that the formation begins due to the formation of due to the adhesive forces, and in case of a circular orifice, by symmetry the adhesive forces cancel out in the lateral direction. So therefore there is no perturbation to create the initial wave. So nothing happens thereafter. And then we tried for triangular and rectangular orifices. Rectangular, we tried a rectangular slit, and in both these cases there was a twisting pattern observed in the shape of the orifice, that is, in the shape of the cross section. The cross section twists while going down. This can be explained by since the water surface tension tries to reduce the surface area to reduce the surface energy, it tries to take the fluid, the steam from a triangular or rectangular shape to a more rounded circular shape. So that's why the twisting also happens, and the pattern is also created. This can be seen. This is the case for the triangular orifice, and that's for the rectangular strip. So in both these cases, the nodes and antinodes are visible. And increasing the size of the orifice. So increasing the size of the orifice, we tried it for both the cases in triangular orifice itself. And in this case also, you can observe that the wavelength is increasing, and also there is a thicker stream of fluid. So we explain this by saying that increasing the size of the orifice leads to an increase in flow rate. So we are keeping the velocity constant of fluid, so it leads to an increase in flow rate. And since in the increase in flow rate also we observe the same observation that the wavelength is increasing, therefore by the same explanation the wavelength should also increase here. And we tried this experiment with the glycerol also, so to basically change the velocity, but glycerol also has many different parameters that are different. The velocity, viscosity is pretty high, so we can comment on that. We could not observe nodes and we could not clearly observe nodes and antinodes here, but the initial characteristics are the same. Like the thinning of the stream suggests that, and the way it is thinning suggests that further down the stream, it may be it is possible that the nodes are formed, but in our experiments, we weren't able to get that much glycerol, and also the rate of flow wasn't low enough to compensate for the increase in velocity by gravity, and therefore turbulence was achieved at the end. So before the nodes were formed. So in conclusion, we in our experiments, through our experiments and the theory that we've given, we were able to identify basic proportionalities like what increases with what and decreases like wavelength and stuff. So that we were able to observe the rate of flow, shape of orifice and size of orifice. We also did it with the tried viscosity, but we can't comment on that too much based on the experiments. And we can also we say that nodes and antinodes are not formed because in the classical definition of nodes and antinodes, there's supposed to be two-wave interference of two waves, due to which nodes and antinodes are formed. That's why maybe the guy said that rejected it instantaneously because there are no two waves forming. If we consider it's only one wave, so that's why we can say that there's no exact nodes and antinodes formed. But these structures are very real; they are not illusions, and but the explanation is not by waves like we traditionally think of nodes and antinodes, but by weave proposed by cohesive and adhesive forces, which is basically surface tension. So I think we concluded that both the parties were correct in their point of view because these structures are real; they are not illusions. So the first guy was right, and the second guy was right because there are no traditionally defined nodes and antinodes here because there is no interference. Okay. And for the properties, for the limitations, we were not able to maintain precisely the flow rate and change the shape of orifice to get precise measurements for getting the accurate relations. So I think we can
1 minute.
do that. I think we can do that better if we're provided correct equipment. And with the explanations that we added for the observations were after we got our reviews for the report, which suggested the same. And to extend the further work, we plan to study the mathematical model of cohesive adhesive forces and how it affects this. And also then we can work on the exotic patterns part of this.
Team Fourmions, you guys?
Yeah.
So 2 minutes. Fine.
Okay, I am starting the timer. 3, 2, 1, start.
So we really appreciate the efforts of experimental efforts of the Gluon Goons, but there are several points to criticize. Like in the presentation, I like to refer that they have said there are no nodes and antinodes. It's a wrong term, but we can have a damn oscillatory equation, differential equation that delta double dash plus 2 gamma in delta dash plus omega n squared delta. This forms the pattern. They have also said that the triangular cross section produces twisting jets, which is wrong. It doesn't form twisting jets. Again, they have said that British man's statement is also right, but it is only right for a critical viscosity value, that is root over rho sigma r n square minus 1 by n, which is a pretty very high viscosity. Their presentation is almost similar to the paper they have produced, so I will now move to the paper. The addressing of the conflict between Keener and British man. Although they have changed the conclusion, but it again doesn't give proper explanation or assumption they have taken. The core mechanism. They have said that the bulging is formed due to adhesion, but once the jet leaves the orifice surface, it doesn't have any contact force. The adhesion is formed due to perturbation. In Uniqueass to show that Rayleigh pattern instability, there is axial curvature which produces that such perturbation. We have added the equation for the perturbation there also. Additionally, they have used the Laplace equation for pressure. But there are two types of radii here, azimuthal and axial. So they haven't mentioned them too. They could have made a mathematical formulation of which they are using explicitly like azimuthal or axial and incorporate the mechanical. The Rayleigh plateau. They have used it, but they have named it, but never used it. You know, the most fundamental mode, the fastest growing mode is in lambda is equal to in 9.01 hour. They have in fact performed the experiment but never measured the radius of the lambda. As they have performed, they could simply use a scale or a Pascal to measure the wavelength, even know the distances, and prove this. They have also taken a statement that with increasing density, the velocity decreases, according to Bernoulli's theorem. But Bernoulli's theorem doesn't state that, but in Torricelli's law, that is derived from the Bernoulli's theorem, the exit velocity is root 2gh. It is density independent. They must have introduced the Weber number, that is rho v squared r by sigma, which constitutes the density. In one line, to incorporate the Rayleigh plateau instability, they have said gravity is absent and linear. And in the next time to explain the phenomenon, they are saying that it's non-linear and gravity is present, which quote unquote creates tapering. So the assumptions are inconsistent. They could have used the equation I've said and incorporate gravity into it, and then form a simulation of something like that. The non-circular orifices, the triangular, rectangular. These are actually stable capillary oscillations, although damped, but these are azimuthal modes that they have never mentioned in the paper. Like omega is root over n square minus 1 sigma rho r naught. They could also have created exotic patterns by forming superimposition of such modes. The circular jet thing. They have said that the circular jet never produces any modes, but is there any explanation in the paper? They could have taken a higher height or a smaller height and see that maybe the nodes are beyond their observational region, or the nucleation maybe flow out with the flow, jet flow, maybe would not. They have created a reacted air curve to observe that. And final but not the most important, the problem asked for mathematical explanations, theoretical explanations along with simulation experiment. There are no solutions present. The experiments prove the qualitative factor, like with increasing R, the lambda increases, but they don't give any proportionality. Like here I've added that lambda raises to R naught 3 by 2.
1 minute, 3 minutes.
They have also never used the main three governing parameters, like Reynolds number, Monesol's number, and Weber's number. Like they have explained that glycerin has higher wavelength than the water, but they could have shown that Monesol's number of glycerol is 30 times more than weight number of water. So it's also they have used they have only confiscated they have only blamed viscosity for it. But glycerin also has surface tension and density different from water, so those can also be the cases. So there are various also the citations they have provided. There are lecture notes. It would be better if they produce traditional literature papers. In fact, the fifth footnote they have given, that's a 404 not found. So they could have used that Eger-Willem of 2008 paper or Raymond's 1879 paper. And that's all. These are all in a brief.
Now we have the fine men, and so you have 2-3 minutes to prepare fine men.
We'll get 3 minutes. So, are you ready? 3, 2, 1, start.
So, the rules their presentation. The presentation has been largely qualitative in nature, with very few any simulation or any examination. This is one of the primary pattern observed in the technique of their presentation. They don't have sufficient data or any verification to confirm their theoretical statement. So I will now mention some plus points in their experiment. First of all, the way that they have created experiments for a variety of situations and used a few creative setups to verify various relationships. They were able to find out quantitatively that the size and wavelength increase. There is an increase in orifice size leads to an increase in wavelength size. An increase in viscosity probably leads to an increase in wavelength size. And it was a really great addition to see. Then go through a full range of flow rates to show factors other than the adhesive tensor factors that they mentioned. So show edge cases where you do not see more than through either turbulence because the flow rate is too less and you just directly see droplet formation. They have also, in the different shape of orifices, they have correctly identified that the circular orifice leads to the laminar flow, and the helical pattern due to the triangular and rectangular orifices was also interesting to see. But ultimately, they have not provided any precise mathematical model nor any precise experimental data. So, as for the critique, it stems from the fact that again they have not provided any experimental data, and the critique claims that the adhesion model that they have used, because after the liquid is already flowing, there are no other surfaces for any adhesion to apply. So I agree with the critique. The adhesion model is probably not justified well enough, but they are justified well enough. Next, so they have mentioned the Rayleigh plateau instability. It didn't feel like that they have actually properly used it anywhere in the application, and I agree with the critique. Furthermore, the critics have also said that the citations are apparently broken, but I have checked that is not the case. The citations work. And moving on to their citations, where they have lacked experimental data, they have actually reinforced their work. They have made up for their shortfalls by citing appropriate literature. As in the case of the various theoretical frameworks that they were mentioning, in particular, they have cited a paper to the Rayleigh plateau instability, and while they were not able to experimentally demonstrate the prediction, they cited it. Thank you.
Fine, Mary. You have. I mean, if you are ready, the presentation you can go on. You have. If you want to prepare, you can have 5 minutes.
You just take some. Ready? Yeah. 12 minutes. 3, 2, 1, start. So, good afternoon, everybody, and dear judges. We are Team Feynman. I am Brian. This is Savir, and the team members Dishant and Veena. We were working on question number 2, and this is our project. Basically, what the question is asking is that there is a cup, and someone is pouring a liquid out of it. What you would usually expect is that the liquid pouring out of it would create a perfect cylinder by intuition, but that's not exactly what happens. What you see is that when the liquid is poured out, then the liquid forms these weird waves in the air. Now, this was the claim of Kinay-Washing, and the other claim was given by British Manbakta is that these waves do not form, and that is just a figment of his imagination. Now, we are here to see whether these are actually forming or not. First of all, I would like, before I go into our theoretical modeling of it, I'd like to give you guys a very simple explanation as to why this is probably happening. This is happening because if you model an orifice or some kind of hole which is not exactly circular, you have fluids that are coming out of this hole. In the case of the cup also, this is the same situation because due to addition to the cup rim, the fluid wants to become a oval shape, and so it comes out in this shape. And now what happens? We all know surface tension, and surface tension has a full relation so that the change in pressure across a boundary is related to the surface tension into the gradient of the normal rate. So you can clearly see that the pressure gradient will be dependent on how much is curved. This will be equal to 1 by R1 plus 1 by R2. So in regions like this, where there is much more curvature, you see that the curvature is more, that means the radius is lower, hence the delta P is greater. There is a greater inward force for the liquid inside than in these places where the curvature is smaller. Hence, we see that this shape will now evolve into something more circular. because that is the minimum surface area that is possible. This is we are talking about in each cross section of the fluid itself. Okay. Now, what happens is that because of this force, now when they reach the circular formation, these particles have a greater velocity than these particles. Hence, it now overshoots, and we get something like this, and the cycle continues. This you can see over here, which we have tried to model very simply by noticing instead of having one stream, if you instead had two cylinders of water falling down, and if you try to bring them close, due to the surface tension interaction, you will form this kind of shape distribution. This is not the exact situation, this is just a visualization. Okay. Now, we go into the actual derivation of what we did. Before that, we will go into the assumptions, which are standard assumptions that fluid viscosity is very negligible, and phi, which is like the velocity potential, the square the Laplace of that is 0, which gives the Laplace equation. Now we know how to solve the Laplace equation using what we usually do in electrodynamics as well. We'll go into that in a while. And also we assume something which sounds a bit weird right now, that the axial velocity through the fluid stream is constant. You know there is gravity, but we'll get to that. We assume it constant for now, and also we assume there are small perturbations or noise. What are these perturbations? Anything which is outside of a circle, we consider a perturbation. So this, if this is a circle, this is a negative perturbation, this is a positive perturbation. Okay? Now, when we try to solve for this, what we assume for the solving is that as it's a laminar flow, this is also one of our assumptions, we find that the radius at each point in this cross section is equal to r naught plus, because we can decompose it via Fourier series, because it's a continuous by laminar flow. So we say some perturbation depends only on the column height from the orifice, because obviously the shape does not change with time. You can think of that because one particle's the amount of force that it experiences over time. Another particle at a different time will also experience the same forces and hence get the same shape. So the shape itself does not change with time. It stays constant. So it only depends on z, and we have a term like this, and it's a summation. Now initially, because it's an ellipse we are assuming, in that ellipse n will equal to 2. And hence we, if we plug it into the formula for radius of curvature in polar coordinates, we can basically solve for the Young-Laplace equations and get this formula out for Az, which A2 is written here, which is the perturbation. Okay. And you find that the perturbation has a what do you call it? An harmonic oscillator form, and you get from this a lambda, which is formed from the omega square equation. And we see that by this elliptical derivation, the column that is falling, the lambda that it has, is proportional to the velocity, proportional to the root of rho, which is the density of the liquid, to 3/2 of the initial radius. Now, how do you define radius in equations? We'll get to that. And also sigma, which is the surface tension. Now, except for this, there is another regime that's happening at the same time, which is also due to surface tension and also due to the Young-Laplace equation. And this is caused due to any variation or any perturbation in the liquid column. This is known as Rayleigh instability. If you have any variation like this that we talked about, these variations will also contribute to some kind of force. Okay. Now, if we because when the liquid is falling, it does not immediately reach steady state. There is some time variation in each section, and we model it as that equation there. Okay. And from that, if we, this is not a solution to the equation. We have assumed that there is some there is some time dependence, and we see if that time dependence exists by plugging it into the equation. And when plugging it into the equation, we see that when kz r naught, kz is basically the wave number for the wave that we're considering here, is less than 1, that time there is some, this is not an oscillatory motion along the axis. Okay. This is along azimuth, this is along the axis. It's not oscillatory and instead blows up exponentially. And at some point, this is very interesting, this is the unique thing that we got out of the presentation. There is a point when that perturbation is no more negligible, and at that point A2 becomes equal to the radius of the initial stream. And at that point what happens, the flow completely stops because it pinches into the liquid completely and there is no more flow. So now what happens is you have these small droplets which are forming. Instead of this wave, this completely blows up and you get these small droplets that come. And this is what you call Rayleigh instability. Now, very weirdly, if you now take the ratio of the length before this happens, and you call it L breakup, and you divide it by the lambda of the oscillations, you will get a ratio which exactly tells you that if this ratio is less than 1 or close to 1, then one wavelength after it already breaks up and then you do not see anything, right? So that is Butter's regime, and the other one is Grenier's regime, in which you actually see significant amount of oscillations. Now we will quickly go into the simulations that we did for this. We used a software known as OpenFOAM. It is a open source fluid simulation software. It does not really it uses your standard Navier-Stokes equations, and we plugged in these specific conditions for the standard case. These are not very visible here, but you can basically set velocity, the shape of the initial orifice, and also the density, the sigma, which is a surface tension coefficient, and all other things you can set on. Once we do that, we see these graphs which are forming. Here, this is the control case, and we vary basically each parameter. Here we varied the velocity to be twice the velocity, and you see that the nodes have now twice the distance, which is experimentally, which is given by the theory. And here also, if we increase the density by 2, you get that it's root 2 times the lambda, which is also given by our formula. So this experimentally verifies the formula, and this is a cross section of the stream itself, which gives it. This red region is basically velocity of the particles going out of the stream, and blue is going in. So these are the perfect nodes that are being created. And here is a Rayleigh instability region that is being created. Now we go to the next slide, and now we plugged in real values as well. We actually did the experiment. We varied density by using water instead of ethanol also, and we checked for the exact nodal distances, and we put it into the formula, and we found out that it has an error of around 9%, which is pretty good for a not very crude experiment. And the simulation had an error of around 1.2%. This is something which was pointed out in our critique. And also we use some exotic shapes. This is basically a slit which has a weird curve. Instead of this, it has some a component here and some component here. So it forms a spiral shape instead of forming the traditional shape that we're talking about. Now, finally, we are acknowledging the limitations of the setup. First of all, gravitation. We said we neglected it, that V does not change with distance. It actually does. But if you plug in the continuity equation, which is AV is constant, and you derive what the gravitational relation will be, it depends as V to the power 1 by 4. So in the very small region where the oscillations are noticed, the change in the lambda is very negligible. So it kind of gives you the real life interpretation. That's why also the errors were positive, because gravity pulls down the wavelength, and that's why the wavelength is larger. And future prospects are that we will try to incorporate more exotic shapes of the orifice itself, and also these simulations like this are very important for like rocket engines and stuff, because of the fluid that are being ejected out of their bottom. So you need to study that and these nodes as well. And so finally we come to the fact that because of that resultant, when the breakup length is a long region away, you will be able to see a lot of these wavelengths before it breaks up. And that's what Uniqueass was observing. This is something you notice when you are R0, because we derived that formula as well some time ago. This formula, so it depends upon your R0 and with your epsilon, which is your initial like perturbation. So if your perturbation is low, you will have a lot of these wavelengths, else you will have a low. This derivation is just done by dividing the two formulas. It's not. So, and by the end, yeah, and the other one is when it's close to 1. And these are the citations for the entire thing. And basically that's the presentation. Okay. Just did you have a 1 minute?
Yeah, we had 50 seconds left.
Can I just quickly show you guys a simulation that I did also for the thing itself?
Yeah, fine. Yeah. So 50 seconds.
Yeah. We start, don't start.
Okay, yeah.
Okay, if I sorry.
It is not visible.
Can you see now?
Yes.
Okay. If I go into this is our actual simulation. If you run it with time, you'll be okay. This is the stream itself. You can see the orifice shape on the top, and this is the stream. If you let it run with time, you will see that the evolution of the jet as it goes. Here we have used the control setup. It takes like 30 minutes to load different setups, so we have not shown the other ones. And this is like the velocity. So you see in this region, the velocity is going out. Here it's going the negative direction, so you can see clearly that the thing is coming in and then going out again when the signs of the velocities change. So this is confirmation of what? Okay, that's it.
Uniqueass Theorem. Theorem, guys. You go? Yeah. You all have 3 minutes to be ready, right?
Are
you ready? So
7 minutes.
Yeah. 3, 2, 1, start.
Okay, so we are doing Uniqueass Theorem and we are criticizing Team Feynman's report. So one of the points that we found was a flaw that the problem statement is using a glass to pour water out of the glass. So he observes his anti-nodes and nodes. The problem is that in that orifice there is a D-like shape and the amplitude of the log-wise radius is actually larger in that case. So the linearization of Laplace approximation may not work in that case. But the report does not take into account any non-linear terms or does not give any verdict on that. Second point is that they could have studied effects of viscosity a bit more and how it causes damping and the antinodes and nodes might collapse before even breakdown happens. Third point is that they could have used a clever number to unify some of the variables and justify why water jets break down at higher velocity. And one more point in the experiment they did, they justified that using ethanol they obtained a larger value of lambda, but they only said that they got that because of surface tension but did not take into account of density. That is one of the points we found. Yeah, that is. Thank
Be ready for your review. Schrödinger, hello. Schrödinger, how much time you need? Can I? Yeah, 2 minutes. That is.
Are you guys ready? So you have 3 minutes of time. And so 3, 2, 1, start.
So we came Schrödinger's dogs and we'll be reviewing Feynman's presentation. Basically about the presentation, they had a really strong mathematical foundation, like using Young-Laplace's equation for the harmonic oscillator, differential equation, and also using the Rayleigh-Plateau instability. That was really well laid out. And they also clearly stated their assumptions and they really compared the experimental and simulated data really well. And usage of the open source of 24 3D for the Navier-Stokes simulation was also really good. And that was a really nice way of validating the model. And they also showed variation in the wavelength of the pattern by changing different parameters. And they also listed out their limitations properties. And the conclusion that they gave was really good for 2 different cases, how the patterns would change. And yeah, that was about the presentation. And coming to the critiques that was given. So one thing that they mentioned was the linearization of the Young-Laplace equation. And they mentioned that we might get non-linear terms for larger orifices. And that's a valid point. And yeah, the concentration of ethanol used was also not mentioned in the experiment. That is one point. And yeah, they could also try out different liquids to check out how viscosity alters the wavelengths of the pattern. And yeah, and the use of Weber number, which might have given the transition between the carbon form and the droplets at the end. So, yeah.
We will first announce the best report and the best presentation and the winners. Okay. So the best report is from
Projectile Dysfunction. Now we are coming to the best physics fight presentation. So that goes to
Okay, we are again very highly organized committee. Okay. The best presenters are
the Feynman.
And now the highest overall score
goes to.
Any guess?
The Feynman.
It is the Feynman. Oh, we come. Where is the fourth member?
Yeah, मैं बोलता हूँ ना अब फिजिक्स फाइट कर रहे
फोटो को ले लो
अबे ले यार इतना क्या सोच रहा है
Ensemble next one अरे 4 लोग हैं भाई
अरे ठीक है करो तुम
अरे ये बजट कहाँ से आ रहा है
पॉकेट से
जेब से
Run actress.
Yeah.
Right.